Hi folks, we're going to take a look at number 11 on page 347. So what they're asking us to do is to determine whether there's any values of m, which represents some constant, for which this equality is true. Okay, so the first thing I want to do is see if there's any restrictions on what m could be. So here we know that the input of a logarithm has to be positive. So here if I look on the left hand side, m and x have to both be positive or both be negative. Okay, in order to make the whole thing positive, neither of them can be 0. Problem is when I look on the right hand side, x can never be negative because the right hand side has to also be true. So that means if x has to be positive, m must also be positive. So I'm only interested in values, first of all, that are greater than 0. Now right away I can actually see a value where this is going to work. Okay, what if we let m equal to 1? Okay, then what do we have? We have the left-hand side is equal to log of 1 times x, and here we have the right-hand side is equal to 1 times log of x. So here we have log of x and log of x. So left-hand side equals right-hand side. Okay, so we know that there is a value, m equals 1, for which this is always true. Question is there any other value of m for which this might be true? Okay. Now, my first instinct is to say no, because if I take log of mx, I know that this can be written as log of m plus log of x by our first logarithmic law. Okay. And I don't think that this is going to be equal to m times log of x. Okay. Having said that, I need something a little more precise than just a feeling here. And I'm not quite sure where I would go with this to try to give an algebraic justification, because I clearly can't check every single m value. So I'm going to have to find a way to give a justification. So I think they suggest that we can also use a graphical reasoning here, and I think that's what I'm going to do. So remember that m represents a constant, so m is just some number, log m is just some number, but x can take on any valid value, okay, in this case here, anything that's positive. So this, I'm going to think of log x as being a function, this log x as being a function. So I'm multiplying, so let's look at this right hand side. I'm multiplying log x by some number. So graphically, this can be thought of as a vertical stretch. So let's think about what log x looks like. Okay, it looks something like this. Okay, and if let me get a different color here. If I do a vertical stretch, okay, if I stretch this function vertically, what's the one thing that doesn't change? Anything that's on the x-axis will not change. So this point will be invariant, but everything else will be stretched. Okay. And since m has to be positive, which we already determined, I know there can't be any flips going on. Okay, so I know that this expression would be represented graphically by this blue function. Okay, unless m was equal to 1, in case it would just be, in that case it would just be log x. But we've already dealt with that. Let's take a look at this here. Here I have log x plus some fixed number. Okay, this is represented graphically by a vertical translation. Okay, so again, if this is what log x looks like, here I'm adding, okay, and when I take, log of some number, I'm either adding, or I guess I could be subtracting, but in the end, I'm performing, okay, because log m could be negative, I'm performing a vertical translation. And what happens when I do a vertical translation? Everything moves up and down. So that means this new function can't pass through 1, 0. Okay? It has to be different from the one we have here. This one will still pass through 1, 0. This one here, whether it's moving up or down, cannot pass through 1, 0, because all points are shifted up or down. And I think that gives us our graphical reasoning as to why these two things are not going to be the same unless m is equal to 1. Okay, I think that's it for this one.